Hello, my name is Agustin Zuniga. I am a doctoral student at the University of Helsinki, and I will present you our work that systematically evaluates the performance trade-offs and privacy and deployment costs of low-resolution thermal array sensors for occupancy detection. Human occupancy information is essential to implement building management systems, as they give a basis to optimize energy use and ensure comfortable and healthy indoor environments. A common method to collect this information is low-resolution thermal sensing. Here you can observe an example of a sketch of a person entering through the door using this type of sensors. The high diversity of sensor arrays and camera configurations make difficult the deployment of solutions that balance performance, privacy, and cost. We can see, for example, that while higher frame rate provides more data, it also introduces a higher temperature difference per pixel. Also, while low resolution reduces cost and privacy issues, it increases the complexity to estimate human occupancy. With this in mind, our work provides guidelines to improve occupancy estimation using low-resolution thermal sensors, while minimizing privacy issues and deployment costs. Our analysis facilitates the use of this type of sensors to support real-world deployments. To understand performance and cost variations, our work focuses on evaluating different frame rate, resolution, and viewing angle configurations. For the analysis, we use an open source dataset and a proprietary dataset from a control testbed. Both were collected using thermal sensors of the same model and make, but with different field of view. A generic pipeline for occupancy detection using thermal sensors was used to perform our analysis, and it included a preprocessing part that reduced the inaccuracy caused by internal heating of the thermal device and the misalignment of the resolution between thermal and RGB images. A detection and tracking module that used simple algorithms that detect blobs using multiple thresholds and track them using position logs. And a flow counter module to estimate occupancy based on the flow and transition of blobs. All of these allow the evaluation of a higher amount of camera configuration and getting the guidelines to select low-cost thermal sensors. In the case of frame rate, different configurations were prepared by considering only every n number of frames from the original video. Our results show that frame rates between 4 and 16 generally perform very similarly and don't have a significant impact on the overall performance of the occupancy counting algorithm. We also observed that frame rates below 2 result in significant decreases in accuracy. However, resolution also has an effect. In our work, different resolutions were obtained by calculating the average temperature of multiple pixels and then combining them according to a drop factor. Resolutions higher than 4 times 2 perform very similarly, especially when frame rate is at least 4 frames per second. A resolution of 2 times 2 can also offer reliable detection but requires higher frame rates. In terms of privacy, 4 times 2 resolution reveals very few insights about occupants' identity or behavior. Also, using low resolution decreases manufacturing and operating costs and makes the solution easier to adapt. Finally, different viewing angle configurations were prepared by cutting the pixels from the sides of the image. We consider two types of angles. The first type is parallel to the walking path. Here, all the resolutions have a good performance where the viewing angle is between 42 and 55 degrees, and a frame rate is at least 4 frames per second. The second type is parallel to the door frame, where the best results occur for viewing angles between 50 and 75 degrees using a resolution higher than 4 times 2. In general, high resolution provides a wider range of viewing angles, covers a wider area, and is more flexible in sensor alignment. Low resolution, however, requires the sensor to be very carefully aligned over the entrance. In this article, we provide a novel insight about the use of thermal sensors for occupancy detection. The effect of having different camera configurations showed, for example, that even low resolutions is more than sufficient to estimate accurately occupation, as long as the sensor is well positioned, aligned, and has a high frame rate. We give guidelines on how to select the best sensor technology for a given deployment. For example, in real-world deployments, the use of low-resolution sensors can reduce deployment costs in about 97% and mitigate privacy issues. Overall, we contributed by positioning low-resolution thermal sensors as a potential solution for supporting building management systems. You can find more information about the implementation and the results in our paper. If you have any questions, you can contact us by email. We'll be pleased to answer. Thank you for your attention.